Hello, everyone. My name is George Hadjidemetriou. I'm a postdoctoral research associate at the University of Cambridge, working for the Asset Management Group and the Cambridge Center for Smart Infrastructure and Construction. The presented work is a collaboration with my colleague, Manuel Herrera, and our supervisor, Ajith Parlikad. The topic of the presented work is road network layout planning based on evaluation of connectivity and asset criticality. This is the agenda of the presentation. I will start with presenting the background, including the research gap and research objective. And I will continue with the methodology and the application of the methodology to a case study in Portugal. At the end, I will present our main conclusions, contribution to science and to practice. Transport networks are an essential element of any country's economic progress. Good transport equals more than 3,000 billion kilometers yearly only in the European Union, while passenger transport equals around 6,000 billion passenger kilometers per year. Most of these movements are happening over road networks. A very critical and also vulnerable element of road networks is bridges. Bridges are normally positioned at intersection of road networks. The current study focuses on roads and bridges. European transport infrastructure networks are at an insufficient condition due to low investments, and this means higher risk of accidents, lower performance and availability. A possible disruption can cause loss of reachability to areas of interest, traffic rerouting, and in extreme cases, fatalities. State of practice in transport infrastructure asset management and planning can be defined into different stages, but every transportation department follows their own procedures. So this figure only generalizes some of the main steps. So asset management and planning can start with condition monitoring, which is normally conducted manually or semi-automated, and it's followed by the use of asset deterioration models. Then authorities use cost-benefit analysis to identify what's the optimal time for applying maintenance and renewal activities. After that, or in some cases at the same time, they try to evaluate the resilience of existing infrastructure. Based on this evaluation, if they have enough budget, they plan a new network layout. The last two described stages face some major challenges. Decision makers need to follow a network perspective due to failure propagation and traffic rerouting. If an asset fails, it affects other assets of the same network, or even assets that they belong to different interdependent networks. Additionally, there is a significant variation amongst nodes and links criticality due to the traffic that they serve and the impact of their failure. There is no standardized technique for assessing resilience and for planning a new network layout. Resilience can be defined in different ways. One of the widespread definitions of resilience says that it is the capability of a network to prepare for, absorb, recover from, and adjust to disturbances. Another definition for transport resilience is that it is the ability of the network to minimize operational loss. When adapting a network perspective in managing and planning transport infrastructure networks implies that we understand the different levels of asset criticality and what network connectivity is. According to the literature, resilience and network connectivity are directly connected. However, we identified a research gap. There is no standardized method for evaluating network connectivity and for planning an optimal network layout. Thus, the objective of the presented work is to develop a network connectivity assessment method and also to propose the development of optimal alternative routes in order to improve connectivity and resilience. The methodology we followed can be divided into three main stages. The first one is called Spatial Network Extension, and it describes how we develop our complex network, which includes the existing network and potential new roads. We use two different types of nodes. Nodes A describe municipalities and nodes B represent bridges. Also, we had two types of links. The links with solid line represent existing roads, and the links with gradient line represent dummy roads, which mean potential new roads. We use the rule for the development of our complex network. Dummy links should not cross with existing links. The second stage of our methodology is network connectivity assessment using our own developed measure term ABA closeness. Closeness centrality is a technique that already exists in network science, and it approximates the distance between a node and the rest of the nodes of the network, and thus the level of isolation of the examined nodes. If we have high distance, then we have high closeness centrality measure, which means poorly connected nodes and high levels of isolation. ABA closeness, which is our own measure, approximates the distance beginning from node A, which in our case is a municipality, passing by a node B, which is a bridge, and finishing at another node A, so another municipality. We use geographical distances measured in kilometers. The third and final stage is the optimal road section selection. It is based on a modified genetic algorithm that we selected because genetic algorithms, they can solve problems with large solution space, and they also use a binary alphabet, 1 and 0. In our case, 1 is existing roads, so existing links, and 0 is potential new roads. The outcome we get from the genetic algorithm is a set of k new roads, which are proposed to optimize ABA closeness and thus improve connectivity and resilience. The new roads are chosen among the set of all new potential roads, and the number k of new roads is set by the user, and it is based on the budget and on physical and environmental constraints. Regarding our case study, we used Python and NetworkX library. The processing time was 2 minutes on a normal computer. The data is from Infrastructure of Portugal, which is the organization that manages roads and railways infrastructure in Portugal. Our complex network had 21 bridges and 12 municipalities. On the top left, you can see the map. With green color, we have bridges, with white color municipalities, and we can also see the roads that they connect them. On the right side, we have the developed complex network. With blue color, we have municipalities. The size of these nodes is proportional to their population. With yellow color, we have bridges. Black colored links are the existing roads, and gray colored links are the dummy roads. we ran our code for 2 cases, 3 newly developed roads and 5 new roads. For 3 new roads out of the 68 options of dummy roads, the optimal combination give us reduce the ABA closeness from 0.57 to 0.35. And for 5 new roads out of 68 dummy roads, which the possible combinations are more than 10 million, the optimal combination give us ABA closeness of 0.31. In the figures, you can see with red color the proposed new roads. Here we have 3 and here we have 5. To summarize, adding a limited number of optimal new road sections can significantly enhance connectivity and thus resilience, even when our budget is limited. And we can see that because adding 3 roads didn't make a lot of difference compared to adding 5 new roads. 3 new roads were enough for the examined network so that we will significantly improve connectivity. The contribution to science can be summarized by our own developed ABA closeness measure, which assesses network connectivity, and by our modification of the genetic algorithm for proposing optimal road sections to be developed for improved connectivity. Contribution to practice and society. First, the developed technique can form the basis for transport networks connectivity assessment, helping in this way decision makers to manage and plan their infrastructure. Secondly, improved connectivity means improved network resilience, decreased traffic delays and associated costs, and enhanced users' experience and safety. The presented work is work in progress, so it has some limitations that we are working on them so that we overcome them. The current focus is links connecting municipalities passing by the vulnerable element of bridges, but in the future we plan to add more links and nodes to our networks. Also at the moment, the user sets the K number of newly developed roads. As we've seen, it was 3 and 5 in our case. In the future, we plan to propose novel road development based on the available budget and based on the road's development cost. At the moment, we examine connectivity. We also plan to add vulnerability, which will multiply the possibility of failure with the impact of failure. Finally, we plan to apply our method to other network types. For example, it could be a multi-layer network, which will include both road and railway networks. The presented work is part of the European Union funded research project called Safeway, which is about infrastructure management for optimized response to extreme events on terrestrial transport networks. By extreme events, we mean either natural disasters or man-made events, and terrestrial transport networks are roadways and railways. Thank you very much for your attention. Please let me know if you have any questions.